All right, thanks. I'm going to be talking about the collaboration between Abernathy and Malheur Wildlife Refuge that examined if we can use electricity from electrofishers to kill invasive common carp embryos. So common carp are one of the most popular food fishes in the world, so it's no surprise that they've been introduced worldwide. They also have a widespread distribution in the US where they've been introduced. We're going to be focusing there at Malheur Lake in southeast Oregon. So common carp are one of the most devastating and effective invasive fish in the United States, and that's due to multiple reasons. One is that these fish are very fecund. Average size female can lay about 30,000 eggs, and a large one can lay well over 1 million. And once development starts with these fish, they grow very, very quickly. The other is that these fish are ecosystem engineers. They can take a clear water environment that's full of emergent aquatic vegetation and in some cases turn it into a cloudy water environment that's devoid of vegetation. This is done in part by their foraging. They forage in the sediment of lakes and streams, kicking up sediment. When they do this, they uproot the emergent vegetation. They also make the water cloudy so it's difficult for it to grow, and sometimes they can eat this vegetation. Secondly, they can change nutrient cycling in these systems through a couple different ways, including excretion of waste directly into the system and also through resuspending nutrients when they're foraging. The result of this is that carp fare just fine because they're generalists that tolerate poor water quality and they tolerate eutrophic conditions, and oftentimes they can come to dominate these type of environments. So Malheur Lake is a large closed basin lake in southeast Oregon. At this lake, carp became established in about 1952. Some very important emergent vegetation disappeared as early as 1955, and these changes resulted in waterfowl production being reduced to 10 to 20% of historic values. The refuge over the years has dealt with this by trying to apply rotenone to the lake. It's a fish poison to kill common carp. However, despite these efforts, long-term numbers of carp haven't really changed that much. And in retrospect, this isn't much of a surprise because many efforts at poisoning carp in lakes like this throughout the US or removing them have not been very successful. Recent work has suggested that what governs if these efforts are effective are the recruitment of younger carp into adulthood, hence our focus on killing carp embryos. So electricity is often used as a tool in fisheries, mostly in management and conservation efforts through electrofishing and capturing of fish to count them or mark them. But electricity has also been used to remove invasive fish and also been used in the form of electric barriers to restrict the distribution of invasive fish. How fish react to electricity has been pretty investigated pretty extensively, especially in adults. Factors that influence how they react to electricity include the conductivity of water that they inhabit, how long they're shocked for, how many times they're shocked. We're going to be focusing for this talk mainly on the actual waveform characteristics of the electricity and at what point in a fish's development that they're shocked. As I mentioned before, most of this work has been focused on adult fish, but recently there's been interest in how electricity affects embryos, both from a conservation perspective of avoiding harm to non-target embryos during electrofishing, but also from the perspective of control, killing or containing the embryos of invasive fish. But there's a number of potential challenges with carrying this out. One is that smaller embryos like carp are more resistant to electroshock than larger embryos like salmonid embryos such as steelhead. The other potential challenge is the conductivity of Malheur Lake. Conductivity is the main factor that governs how fish react to electricity, and the conductivity of Malheur Lake is really variable spatially, seasonally, and annually. So we're not really sure what the conductivity is in these spawning locations. So the question we have, one of the questions is, do conditions conducive to killing these embryos coincide with these spawning areas? Carp spawning in Malheur Lake usually follows spring high water in May and early June, driven by snowmelt off Steens Mountain. And this high water may reduce water conductivity in the lake. However, low lake water conductivity can be a problem. At low conductivities, when you shock a body of water, not much power is being transferred to the fish. So when conductivities drop below the actual conductivity of the embryo or the fish, not much power is transferred. But conversely, high lake conductivities can also be a problem, because if you're trying to maintain a voltage gradient in a body of water to kill these embryos, as the water conductivity increases, you have to increase the amount of power you apply to the water. Basically, what I'm getting at with this is that at high water conductivities, you can outstrip the capacity of your electrofisher, and this became an actual concern for us very early before we even started this project, because we took some readings at some potential spawning locations in Malheur Lake, and we found very high lake conductivities in July of 2100 to 7100 microsiemens. So our goal was to basically take a portable, controlled experiment on the road to Malheur and see if we could kill embryos with electricity. And we wanted to expose the embryos to waveforms emitted by commercially available electrofishing equipment. Some waveform characteristics that can vary are frequency and pulse width, but these can usually be easily manipulated on this type of equipment. So what we wanted to focus on was the shape and polarity of the waveform and the intensity or voltage gradient of the waveform. We initially had 3 candidate waveforms we were working with. However, we did a pilot study with steelhead embryos and found that one of those waveforms was not very effective at killing embryos. So we were left with 2 waveform types. One is an alternating current waveform, where the waveform alternates polarity, but it's not pulsed. And the other is a square pulse DC waveform that polarity does not alternate back and forth. So to create these waveforms, we used a couple of pieces of equipment. One was a Colvelt VVP-15 electrofisher to emit the square PDC waveform, and the other was a custom-made shock box we made using electrical transformers to create an AC waveform. Both of these were wired to a shocking chamber, which was basically a small aquarium outfitted with aluminum plate electrodes. We also put together a recirculating tank system consisting of 2 circular tanks, 4 upwelling incubators, and some sump pumps and sump tanks, and we took this with us to the refuge headquarters. Once we were there and conducting the experiment, we refilled this system with fresh water from Marshall Pond daily. So now that we're ready, it was time to capture carp. So we went out to the mouth of the Blitzen River where it empties into Malheur Lake. We looked for carp exhibiting spawning behavior in the shallows, and we netted those fish from shore, checked them to make sure they were expressing gametes. Those that were, we took back to the refuge headquarters and spawned those fish, and then reared the resulting embryos in our upwelling incubators. So we reared these embryos to 5 different developmental stages: blastula, gastrula, organogenesis, active movement, and pigmentation. Once they reached the appropriate developmental stage, we removed the incubating embryos. We counted out about 15 under a microscope. Then we placed them in a shocking basket, placed the basket in the shocking chamber, and we shocked those embryos or sham shocked them for about 30 seconds. Then we placed them in holding tanks to hatch them, and we considered we considered that the embryos survived once they got to hatching. So our experimental design was a fully factorial design where we looked at differences in survival among treatments. As I mentioned before, we had 2 waveforms and 5 developmental stages, but we also had 4 voltage gradients, 10, 15, 20, and 25 volts per centimeter, and a control, and we had 6 replicates for each treatment combination. So here are the results for the first 4 developmental stages. On the y-axis, we have survival. On the x-axis, we have voltage gradient. Over the 0 voltage gradient, we have the control fish represented by a circle. And then over the other voltage gradients, we have diamonds representing the AC waveform and square representing the square PDC waveform. We had low survival at the lowest voltage gradient treatment, 10 volts per centimeter, and we didn't see much difference in survival among the different waveform types, except for in a few situations. And those situations tended to be where we had lower variable control, so I take that with a grain of salt. What's really interesting is that at the latest stage, pigmentation, we didn't reach 50% survival until 25 volts per centimeter, which is really, really high. So can electrofishing be used as a control tool for common carp embryos? There was some encouraging developments. As I mentioned before, survival was low at our lowest voltage gradient. The key here, though, is our water conductivity was really low, and we had higher mortality than observed in other studies that have shocked cyprinid embryos at higher water conductivities, 500 microsiemens. So that's really good news. This disparity in the survival could be due to the fact that common carp have slightly larger embryos than these other cyprinids. Also, we used a larger duty cycle, 50% versus 40%. But much of this difference could just be due to species-specific differences, how fish react to being electroshocked. The big negative here is that pigmented embryos are very resistant to being shocked, and these embryos only took 3 days to achieve pigmentation. So it's a very short period of time, a window of time that we can shock these embryos and be successful. For us to take this out in the field, we have to address a number of unknowns. As I mentioned earlier in the talk, we don't have a really good idea of what the typical water conductivity is in these spawning areas. This one time we measured 135 microsiemens, but we don't know if that's on the low end, the high end, how variable these values are. The other thing we're thinking about is that how water conductivity interacts with lake surface area. So you can imagine as the lake water level goes up and conductivity goes down, this might be good from the perspective of shocking and killing these embryos, but it also increases the surface area of the lake. You might have more area you have to treat. So to successfully deploy something like this, we need to continue identifying preferred spawning locations in the lake and possibly figure out ways to attract spawning fish. Another unknown is, can we maintain 10 volts per centimeter on Malheur Lake using standard boat electrofishers? You can see here this is a standard boat electrofisher setup with 2 booms and the dropper fingers in the water that emit the electricity coming off those. We did a modeling exercise looking at electrofisher outputs, and we found that it's very difficult to maintain this very far away from the fingers with a standard setup. So we're currently investigating if we can get to 10 volts per centimeter with a non-traditional setup like single droppers. And finally, because carp have such a narrow window in which they're vulnerable to shock, it'd be helpful if hatched carp were also vulnerable to electrofishing so we could get more bang for our buck. We're not quite sure about this, but during our preliminary study with steelhead embryos and larvae, we found that swim-up larvae actually regain their sensitivity to being electroshocked, so that's potential good news. And with that, I'd like to thank our collaborators, Peter Brown, who offered us equipment and advice, the refuge staff who helped us with the logistics of the study, and Alan Temple, who helped us model electrofisher outputs. And with that, I will take any questions you have.
Questions in the room?
I'm wondering if you've given any thought to the effect that this may have on other aquatic species, whether it be flora or fauna, and it might be something worth considering prior to applying it on a field level.
That is a great question, and certainly if this project is employed and it sees some success, that's definitely a very important consideration. However, in 3 days when I went out with Linda to collect carp out in the lake, and in 3 days I saw maybe 3 fish that weren't carp, and they were also invasive. So initially it's not going to be a problem.